দেখছো? দেখতে পাচ্ছ?
জি স্যার, দেখতে পাচ্ছি।
ওকে ভাইয়া। ওকে, আমার এটা লাস্ট টপিক ছিল, যেটা আমরা ফিজিক্যালি আসলে কভার করতে পারিনি। তো যেটা আমরা বলছিলাম যে সুইচ ক্যাপাসিটর সার্কিট একটা ইয়ে টপিক। আচ্ছা, প্রথমে আমরা একটু ইয়াকে কনগ্রাচুলেট করতে পারি মনে হয়, না? আমাদের আবরার শাহরিয়ার হচ্ছে আমাদের ডিপার্টমেন্ট রিপ্রেজেন্টেটিভ হয়েছে। সো কনগ্রাচুলেশনস টু আবরার।
থ্যাংক ইউ ভেরি মাচ স্যার।
ওকে, সো লেটস start switch capacitor circuit. Let's see actually what it means. This one you will get in chapter 13, same reference book, same textbooks, Vejad Rajavi, chapter 13. Okay, so very concise and very small syllabus for this one. Let's see what we will talk about here. First, we will talk something about that why actually switch capacitor circuit comes, and then how it works, some precision consideration. That's all. I think mainly three topics will be covered in these sections. So first of all, if you remember that so far we discussed all the amplifiers from electronics 1, electronics 2, VLSI 1, or whatever the amplifiers we discussed. We mainly dealt with the continuous time signal. That means we give an input that is the continuous, like a sinusoidal, and then we observe the output that is also continuous, maybe sinusoidal or 180-degree phase shift uh, signals. So that kind of signal we call it continuous time circuit. Okay, and actually, to be honest, these kind of amplifiers have wide applications, like all types of audio, video, and high-speed analog systems. But beside that, in many situations, we may not get the continuous input. Like we may sense the input only at some specific instance of time. So we call it a sample. Like in a whole period, we take some data for a specific time, not the whole time or whole period. At that time, we call it a sample. Okay. And then the circuit process is sample, producing a valid output at the end of each period. Of course, so we take the input for different time and we get the output also in that way. So this system we call it discrete time, or we call it the sample data system. So this is the main difference between a continuous time circuits and the discrete time or sample data systems. So here we will mainly introduce some class of discrete time systems called switch capacitor circuits. So this is called the switch capacitor circuit. It's actually discrete time system or sample data systems. Okay. The main objective actually to provide you some basic knowledge about this switch capacitor circuit, so that in future you get more advanced topics like filters, comparators, analog to digital converters or digital to analog converters using that switch capacitor technology or switch capacitor concept. So that is the main reason actually we study these switch capacitor circuits. Now, first of all, let's see that how we design a continuous time amplifier. If you remember, this is a basic inverting amplifier, op-amp based inverting amplifier. So if you remember that for a op-amp based inverting amplifier, the output is this: simply feedback negative ratio of the feedback resistance to the input resistance, R2 by R1. So this is the defined by this one, that, or we can say that gain AB B out by B in equal to minus R2 by R1. This one we already know. So, but problem is that this circuit presents some difficulties if we implemented in CMOS technology, like if we use using NMOS or PMOS, because this is using the op-amp. So op-amp can be designed by the either BJT or the MOSFET. So if we use the BJT, okay, this is functions is very fine. But if we use some NMOS or PMOS technology or CMOS technology, then it has some difficulties. So what kind of difficulties we see? That since the gain mainly depends on R2, that means the feedback resistance. So we suspect that that feedback resistance heavily drove the open loop gain. That means it degrades the precision of the circuit. What is the precision? That means perfectness or the quality of the circuit. So with the aid of this simple equivalent circuit, as you can see here, if we see this equivalent circuit of a continuous time system, we can write down this one, this d out by b in or the gain. So this equation actually says that compare the case of R out equal to 0, if we think like this way, R out is means the op amp or the transistor's output resistance equal to gain suffers from inaccuracies in both the numerator and the denominator. So we can say that we have to find out a solution to overcome this. So let's see. Here also in our previous system, the closed loop gain in the previous system, continuous time one, the closed loop gain mainly depends on feedback resistance R2. So what we can do here in order to avoid the reducing the open loop gain of the op amps, the resistor can be replaced by the capacitors, as you can see here. The feedback resistance we replaced by capacitor, also the input resistance we replaced by a capacitor. So what will be the gain? Simple, impedance of the C2 divided by the impedance of the C1. In that case, we can write down that this gain equal to, we can write down, okay, AB equal to minus C1 by C2. I hope you, sorry, minus C1. C1 by C2. Why C1 by C2? Because we take the impedance of the capacitance C2 divided by the impedance of the capacitance C1. And then if we calculate, it will be the gain equal to minus C1 by C2. No problem with that. But problem is that how we set the bias point at this node, that is X. Okay? Capacitor is the storing device. But for the feedback biasing, that how this bias voltage at X we set. So the solution is we may use a large feedback resistor here to set the bias at X. It's providing the DC feedback while negligibly affecting the AC behavior of the amplifier in the frequency band of interest. There is no problem with that. But one problem is here, this kind of arrangement is practical if circuit operates only in high frequency band. But what about the low frequency band? Or if we assume that a step change like this, as you can see, B in, there is a step change here, for example, at this point, that the input step, so response contains at the same way a step change due to the initial amplification, as you can see here. Response means output voltage by the circuit consisting of C1 and C2 and the op amps, followed by tail of this. Because of this, why it is changed? If this is something like this, then it is perfect, no problem with that. But it goes to this way, that means in reverse way, because of the loss of charge in C2 through RF. That is the problem here. Okay? Or we can find out so the condition is there, as I said, that this kind of circuit works only at the high frequency of band of interest because of loss of charge in C2 through the feedback resistance RF. And we found that gain equal to minus RF C1S divided by RF C2S plus 1. So what it indicates? It indicates that gain equal to minus C1 by C2 only if the frequency is much higher, which is defined by 1 over RF C2. Okay? So that is the one difficulties of this one. Next, what we can do, it is possible to replace RF with a switch, as you can see here. Okay? The idea is to turn this switch S to on so as to place the op amp in unity feedback gain and force Bx equals to Bb. That is the ideal op-amp characteristics. If you remember that two inverting and non-inverting terminal voltage, if we can make equal, then the common mode level for the op-amp, that appropriate common mode level of the op-amp, after the switch turns off, node X retains this voltage along the proper operation. That is the one way we can do it. So this is called the switch capacitor amplifier. As you can see here, that this S2 is replaced with a feedback resistance to set the bias at X. There is one input switch to connect the input to the capacitor. Another switch S3, that is the, as you can see here, that is to the ground. As you can see here, S1 and S3 connect the left plate of C1 to input and the ground, and S2 provide the unity feedback. So this is a switch capacitor amplifier, basic switch capacitor. Let's see how it works. This is very important to understand that these three switches actually control the operation of this. First, if we see that S1 and S2 are on, that means this and this are on, S3 is off. What will happen? Yielding the equivalent circuit of this. Hello? Okay. Okay. First, we see that S1 and S2 are on, as you can see, closed circuit. S3 is off. It's given this circuit, that is, we call it sampling mode. Why you call it sampling mode? Let's see how it works. For a high gain op amp, okay, BB equal to B out equal to 0. Don't be confused about where is the BB. If you remember, this is the BB. That means non-inverting terminal voltage, we call it BB. If we consider that BB equal to B out is 0, then the voltage across C1, as you can see here, input across C1, that is appear here as a B in. We say that this capacitor simply samples the input, nothing else. So why it is happened? If this switch S1 and S2 for feedback is closed, then we can find the circuit equivalent to this, where we can say that the voltage across C1 is approximately equal to B in. We say that C1 samples the input. So in this condition, we call the switch capacitor amplifier works in sampling mode. So we can find out here, as you can see here, B in. So BA will be like this. Next, at T equal to T0, for example, T equal to T0, S2 turn off. So that means this is open circuit. Okay, so this is gone. We have equivalent circuit of this. S1 and S2 turn off means there is no input connected with the terminal A. So A is connected, S3 is connected, closed, on. So A is connected to the ground, as you can see here. Since the gain is equal to minus C1 by C2, and VA change from input 0 to 0, as you can see here, so it will go to here. That means it amplifies. So at the first condition, this one we call this in sampling mode. The next condition, when there is no input and A is connected to the ground, then we call it in amplification mode. What is the value of the amplification? That the value of the output voltage is equals to, since the gain is C1 by C2 times the input voltage, that will be input 0. Okay, I hope you understand this. So the switch capacitor amplifier, basic one, it can be operated in two modes. One is sampling mode, where the input capacitance C1 samples the input up to this, but at T equal to T0, if the other switches are on, then input goes to ground, so it will be 0. That means it amplifies, and the output voltage will be the gain versus gain times input voltage. Okay. Now, with these two sampling and amplification mode, we can use a sampling circuit. What is the sampling circuit? The basic configuration of a sampling circuit is a combination of a switch and a capacitor. This is called the sampling circuit. Okay, a simple sampling circuit, which consists of a switch, that is the switch, and a capacitor. Now, the switch can be replaced with a MOS transistor. As you know that all kind of transistor actually or electronic device can be used as a first application is as a switch. So if we use a MOS transistor, can serve as a switch, and then let's see the response of that sampling circuit for different input levels and initial condition. What is the input levels? As you can see here, if we come here, that input level, first input equal to 0, and then we change it to input level plus 1, and also the initial condition, for example, the clock signal, that is the CK, high or CK is low. In both cases, we discuss here, it will be sampling circuit, combination of a switch, and switch is replaced, can be implemented with a MOS, and then the response of that sampling circuit for different input levels either 0 or plus 1, and for initial condition clock signal it can be high or low. So now here if you see this first conditions, the source is connected with the input, that is 0. Drain is connected with the capacitor, and initially we think that capacitor voltage is equals to VDD. And if CK goes high, for example, this clock signal is high, then at t equal to t0, as you can see here, if CK goes high, then we have already have a drain voltage, that is the output voltage is VDD, and then it falls down. Okay, why it is falls down? Because this transistor M1 senses a gate source voltage. This gate source voltage equal to VDD, because source is at 0 and gate is at CK is high. For example, it is a VDD. So VGS equal to VDD and VDS equal to VDD. Why VDS equal to VDD? Because output capacitor, that is the holding capacitor, it already have a VDD. So it is in saturation, and then it has a current. Since it's saturation, it has a current flowing from drain to source, that is equal to half of mu n COX W1L VDD minus VTH whole square. Okay, and then if V out falls from here to here like this, if V out falls at some point, for example, V out equal to VDD minus VTS, for example, somewhere here, then M1 operates from saturation to trial. And then at a certain point, it will go to linear, and then we have a on resistance RON. Okay, so this is the one. Now the next, another condition we apply here, it will be just opposite here, that if we apply a B input voltage other than 0, that is the plus 1 volt, and VDD equal to, for example, 3 or higher value, then we can say this operates in the triode region, and then we have also the same way at t equal to t0, it is the opposite of the previous condition is 0, and then it goes to input voltage equal to plus 1 volt. Okay, so remember this, that a sampling circuit, it's a combination of a switch and a capacitor, and switch can be also implemented by MOS transistors, and then the response of that sampling circuit with different input levels and different initial condition. For example, this is CK high, and here is the CK is low, and also input is 0 here when CK is high, input voltage is plus 1 volt when CK is low, and we have a different characteristics of the response of the output voltage. And next, from here, actually, we call it track and hold capabilities of a sampling circuit. Why we call it track and hold? Track means sampling mode, and hold means we have the same value that it previously reserved because of the capacitor, because it's a storing device. So from here, if we summarize that two important points actually from these operations, in these operations for different input levels and also different initial conditions. So we can summarize that MOS switch can conduct current in either direction. Why we called it? Here you can see if we apply the input at source, it can conduct current from drain to source, that means at the left. But when input equal to plus 1 volt, that means higher other than 0, then the current direction will change from here to here, that is from left to right. So that is, we can say here that MOS switch can conduct current in either direction simply by interchanging the role of source and drain terminals. Second, very important one, that it will act as a track and hold capabilities. Track and hold circuit. That means it has track and hold. What is track and hold? First of all, when the switch is on, for example here, when switch is on, so B out follows B in. That means it tracks. And when the switch is off, here it remains constant. Thus, the circuit tracks the signal if this clock signal is high, and it freezes or it holds when this one is low. That means clock signal is low. So based on this gate signal or the clock signal, it has the sampling circuit has the capability of track the signal and hold the signal. So this is the track and hold capabilities, and the response of that circuit is this. This is something that about the maximum output level. What will be the maximum output level? If we see that in our when we talk about the different input levels for a, where it is this one, the sampling circuit. For the second one, when we use a B input equal to plus 1 volt, so from there we discuss here. For example, input voltage is not plus 1 volt, input voltage is VDD. In previous case, we consider that input equal to plus 1 volt and VDD equal to 3. But in this case, if we consider input equal to VDD, that means the maximum supply voltage is the input. In that case, how the output varies is same as this one. If we use that, what will be current equal to, you know, that C dVdt. So we find it here and find it here, and from there the maximum output voltage we get is this voltage. That is actually VDD minus VTH. Why it is the VDD minus VTH? Because if here is the one is the time is multiplied by this one. So if time is infinity, that means maximum output voltage of a NMOS type of sampler is the VDD minus VTH. So that's why we draw the response of a V out equal to actually maximum is the VDD minus VTH, even input equal to VDD. Now let's see the speed considerations. Speed is actually, you know, that how we define the speed. Simply that time required for the output voltage to go from 0 to the maximum input level after the switch turns on. That is the speed we can say. So if we think about this, that there is a sampling circuit. You already know what is the sampling circuit. Is the MOS switch and the combination of the switch and the capacitors. And then if we see the how we define the speed, that for example, sampling speed is given by two factors in this case. First of all, the on resistance. As you know that RON. Why you call it RON? Because when transistor operates in the triode region, and then we can say triode or linear region, in that case transistor can be equivalent to a just a resistance. We call the on resistance. So speed of a sampling circuit of the sampler is mainly depends on the on resistance of the switch, that means the MOSFET, and the value of the sampling capacitors, that means CH. Thus, if we want a higher speed of this one, that means how fast the output voltage changes from 0 to the maximum input level, that is a large aspect ratio, that means W1L we need, so that we have a RON, and then we have a small capacitors, that means holding capacitor, then the speed of this sampling circuit will be higher. Now some quality considerations, that if we talk about the speed of the sampling circuit, yeah, speed is good, but for higher speed we have to use that large W1L, that means aspect ratio, and also the smaller sampling capacitor, that is the CH. But problem is, these methods of increasing the speed sometimes degrade or decrease the precision with which the signal is sampled. That means the signal we want to sample, but the quality of that signal will decrease because of the higher speed. Because higher speed we only attain if we use the large W1L ratio and also the small holding capacitance. So let's see what is the actually perfect or precision issues. First of all, channel charge injection. This is the important, very important one. Then how it decreases the precision or the perfectness of the or the quality of the sample signal. So first of all, channel charge injection. What is the channel charge injection? If you see here, there is a switch, that is the MOS. Okay. Now, when switch is on, there is no problem. But when it is off, okay, off, then there have a charge that will flow in either direction, either from right to left or left to right. Now, problem is that when it is on, there is a channel. You know that silicon oxide interface, there is a channel between drain and source. So that channel capacitance, sorry, channel not capacitance, charge Q, channel charge is defined by these equations. That is WL COX, oxide capacitance, and you know this one. So W and L has a huge impact on this. But in our previous case, we said that we need larger W over L because of the higher speed. But if you increase the W over L, then charge of the channel will also increase. Okay? Once this is when on. But when this off, this charge, that means QCS, channel charge, exits through source and drain terminals. That is called the channel charge injection. That is the one. Okay. That means when this MOS transistor is off, the charge in the channel was created when the MOSFET was on. Now will exit through the drain or the source. So this is called the channel charge injection. Now, what will be the problem? The charge injected from the left side, to the left side, that means to the drain, it will absorb by the input source. So there will be no problem with this charge. For example, there is a half of charge goes to the left and half of charge goes to the right. So which goes to left, that will be absorbed by the input source. There will be no problem or no error, creating no error on that. But on the other hand, problem is here, the half of charge injected to the right side, that will be absorbed or deposited on these capacitors. Okay, and there will be an error, introducing an error in the voltage state on the capacitor. So if we consider half, that error will be defined by these equations, del V. So what will happen? The regular output signal will be this, and because of the charge injected and deposited on this holding capacitance, we call it a negative pedestal, this one, that will create a error equals to del B, and del B is defined by this equation where you consider that half of the channel charge is deposited on these capacitors. Okay, and from there we see the output voltage is defined by these equations, B input minus that error voltage. Okay, and from here we have find out that. So such thing that the output device from the ideal value, two effects. First of all, non-unity gain, and non-unity gain equal to this, and the constant offset voltage that we found, that this one. Okay, so this is the one problem, precision consideration, channel charge injections. Another precision consideration that is called the clock fit throw. What is the clock fit throw? If you see this circuit, there is a transistor capacitance from gate to drain and gate to source, or we call it actually clock transitions to the sampling capacitors. Clock transistor to its gate drain or the source gate source overlap capacitance. We call it overlap capacitance or the transistor capacitance, gate drain and gate source. So what is the problem here? Then it will also create a error because these overlap capacitance will be deposited on this output holding capacitance or the output capacitance, so that there is a error signal that is defined by these equations, where you can see that these are the overlap capacitance, that is the gate to drain and gate to source, per week, and this one error voltage or the error is independent of the input level. There is no input on this one. Only depends on the overlap capacitance, holding capacitance, or also the gate clock or the BCK. Okay, that is the one problem. Another precision measurement or the consideration, we consider KT by C noise. If you remember in your section A, maybe chapter 7, when you studied the noise, there is a KT by C noise. In that case, we call it, if you remember, there is a, if a transistor charging a capacitor, as you can see here, a transistor, sorry, a resistor charging a capacitor gives a rise to the total RMS noise voltage of, I think you remember, root KT by C. So same problem is actually here, similar effect. Because for a MOSFET, if we think that it is operates in the linear region, then we can consider it's on resistance, RON, and it also has the same similar effect, increase the total RMS noise voltage of root KT by C. Okay, so it also give a problem of the noise. So that also affect the precision of the sampling circuit. So let's see how we can since the main dominating factor or the in precision consistent, that is the charge injection. So how to cancel that charge injection from that switch? There is many ways. So first way we can consider one approach is something like this. If you look at this very carefully, uh, if I see here, okay, look at this. So this is our main sampling circuit. This one, red circle, a switch, MOSFET as a switch, the driven by a driving the capacitor CH. So if you remember that we said the charge injection in both ways, either this way. So in red mark, red arrow, it will be absorbed by the input source. So there is the no error, but only error which one goes to the output node, that will be deposited on the capacitor, that means the output capacitor or holding capacitors. So if we use the charge injected by the main transistor, if we see that M1 is the main transistor and M2, that is we call here a dummy transistor, that will be driven by a clock that is the opposite of the main one, that is CK and CK bar. You see here, okay? So the charge injected by the main transistor, if we see that del Q1 is defined by this equation, is can be removed by means of a second transistors, because this second transistor will create the opposite charge of del Q2, but condition is del Q1 equals to del Q2 so that they can cancel each other. That is the one way we use a dummy transistor of M2, and you see that dummy transistor M2 source and drain is connected to the output voltage, output node. So what is the condition? Condition is that charge injected by the main transistor M1, that will be cancelled by the charge generated by the dummy transistor M2. So del Q1 equal to del Q2, then it will be cancelled. So what is the condition to be similar of the charges? Del Q2 equal to, if this is the equation, then you can choose width of the dummy transistor equal to half of the main transistor, then, and if length are equal, then we can say, okay, del Q1 equal to del Q2. Then this is the one way. Interestingly, this will also cancel the transition, that is the, we call it overlap capacitance. If you see, remember this, then from this one, we have another this. So this will be cancelled to each other. So this is also one more advantage when we use a dummy transistor with the main transistor to cancel the charge injected by the main transistor. It will also beneficial to remedy the click fit through or the overlap capacitance that is injected from the gate source voltage. Now another way we can cancel the charge injection from the main transistor. This is the one very good one actually, better than the previous one. If we use a complementary switch, complementary switch means if we use a one NMOS that will generate inject a charge of del Q1, and we use a PMOS switch that will be driven by CK plus, CK bar, and that will generate a holes of del Q2. Since they are in opposite, so they will cancel each other and no extra charge will be deposited on the holding capacitance, so there will be no error signal. This is the one good way. And the next, last one, I think we have come to the finish. That last one, I hope you know that this is the operates in the differential mode. And in our knowledge, so far we learn about the differential amplifier. The advantage of the differential circuit that the problem of charge injection may be relieved or maybe cancel each other through differential operations. Okay, as you can see here, the B input 1, B input 2, and the charge injected from the M1, del Q1, charge injected by M2 is the del Q2, so that they will go to the opposite and deposited to the output capacitors. But we take the output 1 and output 2, and if we take the differential output, it will be the subtracted one, so that there will be no error signal. So this is another best way to cancel the charge injected by the main sampling circuit. As you can see here, that del Q1, if we write in this way, del Q2 is the same way. We recognize del Q1 equal to del Q2 only if the condition input should be the same for both transistors M1 and M2. So this is how we can cancel the charge injected from the main transistors. So I come to the end. If you go to the here we discussed mainly the switch capacitor amplifier. So please take a good preparation on the switch capacitor amplifier, how it comes using a switch, and switch can be also used as a implemented by a MOSFET. And then we talk about the sampling circuit. What is the sampling circuit? It's a combination of a switch and a capacitor, and switch can be implemented by MOS. And then we see that response of that sampling circuit for different input level and also the initial condition. And then we found that that sampling circuit has the capability of the track and hold depending on the gate input, that means the clock frequency, clock signals. And then we talk about the speed considerations. Higher speed can be achieved if we have a large W/L ratio and the smaller holding capacitance. And then we talk about the precision consideration, that means quality of the sample signal. Mainly three considerations we discussed. First of all, the charge injections by the main transistors, and then overlap capacitance, and then noise, KT by C noise. And the solution, how to cancel the charge injected by the main transistor, there is found some. Then we found that some charge that is injected can be cancelled by some techniques, that is mainly dummy transistors or the complementary switch or the differential mode. So that's all from my side. I hope that you can take a preparation and answer in the final exam. There are some questions also from this topic. Is there anything?
থ্যাংক ইউ সো মাচ স্যার। স্যার আমাদের পরীক্ষার জন্য যদি কোনো সাজেশন দিতেন স্যার, কিভাবে প্রিপারেশন নিলে ভালো হবে?
সাজেশন অলরেডি আমার যেহেতু সেকশন বি, আর আমি আসছি হয়তো 4 সপ্তাহ বা 5 সপ্তাহ আগে। টপিকস অনেক কিছু আছে, হয়তো একটু ইয়ে করে গেছি। আমি যেটা আগে বলছিলাম যে তোমাদের একটা কম্পালসারি পার্ট হচ্ছে ফেজ লক লুপ। ওকে, আর ফেজ লক লুপটা যেহেতু তোমাদের একটু সিলেবাসটা একটু বড়, ওখান থেকে বড় মানে হচ্ছে যে বেশি কোশ্চেন, এটা তো স্বাভাবিকই। আর আছে তোমার ইয়া আছে oscillator, maybe one set, band gap reference also one set, and for switch capacitor circuit and combination with others has one set. So that's all from my side. Is it okay?
Yes, sir. Thank you, sir.
Okay. Even though if you feel any difficulty, just knock me. We can come again.
Thank you very much, sir.
Okay, Abrar. I already provided this PDF. Please circulate it to other. Take a good preparation. Good luck.
Thank you, sir.
Okay.
Assalamu
Allah,
alaikum, sir.
Allah Hafiz. Assalamu alaikum.